So now let's do another example. Let's imagine that we've got a cube. And let's say the cube, same side, length A. So let's say that that is equal to 15 centimeters. And so I'm going to take my cube, and it's going to be sitting here, and I'm going to imagine an electric field going straight down. And so the electric field is going straight down right here. And so I could say that is minus 125 newtons per coulomb J. And I want to know what is the flux through the top of the cube. What's the electric flux at the top of the cube? Well, that's pretty straightforward. Okay, it's going in, so that really should be negative. Okay, and it's just going to be equal to minus EA. So, absolute value here. So I'm going to take absolute the magnitude of E. So that'll be minus 125 Newton per Coulomb. Okay, times A squared. So that's going to be 0.15 meters squared. And so the flux into the top is going to be minus 2.81 Newton meters squared per coulomb. Okay, so I've got my cube here, and the electric field going straight down, so going into there. Okay, I said at the top, the flux was a minus 2.81 Newton meter squared per coulomb squared. So now I want to know what's the flux through the bottom. Okay. Now there's an easy way and a hard way of solving this. The hard way would be going back and doing exactly the thing I did. The easy way is to say, wait a minute, all these lines go straight in here and straight out the bottom. So they go in the top, they go out the bottom. So it's the same area at the top, the same area at the bottom, same electric field. So it's just going to be the same as before, except it's going out. So the flux will be positive. So that gives me the flux in the top and the bottom. Okay. Now, for my same cube, I'm now going to have the electric field coming in at an angle here, and the angle is going to be 35 degrees away from vertical. So I want to know what is the flux in the top. Well, now it's going to be EA cosine of the angle. The angle is how far off it is from being vertical. So the flux in the top is going to be E times A times cosine of 35 degrees. So that's going to be 125 newtons per coulomb times 0.15 meters squared cosine 35 degrees. So the flux in the top is going to be equal to a minus 2.3 Newton meter squared per coulomb. What about in the bottom? Well, the electric field lines are still hitting the bottom with the same angle, so that's going to be also minus 2.3 Newton meter squared per coulomb, except it's going to be a positive because it's going out the bottom. Now, the next question is, what about the side? So what would be the flux through the side? Okay. So if you look at the flux of the side, then that's going to be EA cosine of the angle from the side. Well, what's the angle from the side? Well, that is angle of 55 degrees. So that means that it's going to be equal to 125 newtons per coulomb times 0.15 meters squared times cosine 55 degrees. So the flux through the side is, this is the left side, that is going to be a minus. Why minus? Well, because it's going in that side. Minus 1.08 Newton meters squared per coulomb. Okay. Now, what about the flux on the right side? What's that going to be? Well, the flux on the right side will be positive 1.08 Newton meters squared per coulomb because it's going out the right side. Raises yet another question. What is the total flux here as the electric field's going through? Well, it goes in one side, so that side is going to be negative. It comes out the other side, that's positive. The same electric field lines are going through, so what happens is the total flux is going to have to be zero because you have the same amount of electric field going in as going out. And this is another way of thinking about it. The flux is kind of like figuring out the amount of electric field going in or out. So that's another way of considering what do we mean when we talk about electric flux.